Hello everyone. So we are going to continue what we have studied in the previous one. Now, the statistical inference that we have studied in the previous lessons was mostly about how to do point estimation, how to do interval estimation and stuffs like that. But in this one, we would rather go on to the more probabilistic ways. That is, we are going to first study about joint distributions, mostly about multiple continuous random variables and how they are associated with all the statistical probability distributions. Because oftentimes what happens is you might be given two different distributions following a data set following two different distributions, and you might be asked to find some values which are in accordance with a rule. Let's say x and y are two data sets, are from two different data sets, and you might be asked to find the distribution of x plus y or xy or x divided by y and stuff like that. So in that case we would require the joint distribution. So the process to find that and how to manipulate and how to use them is what we are gonna study in this whole lesson. So let me just prepare the session and then I'll write down the topic. Okay, so joint distributions. Now we are going to study a lot of things here. So firstly let us start with this exact thing. Two random variables So what we are going to say here is two random variables x and y are said to be jointly distributed with the joint PDF fxy x comma y such that double integration over the region A f x y x comma y dx dy. So like this is how we are going to solve these problems. Now this is how the joint PDF would be defined. Now this region which we are talking about, this A is a two-dimensional region obviously, and we need to be careful about the region of integration in this kind of problems, because well what we know from this is if omega is the sample space where then what happens is we have by the since total probability is always 1, then equals to 1. So this is because the total probability is 1. So this is how we are basically trying to shape things. Now this kind of problems might be tricky at first sight, so that is why we would be doing a few examples to make sure that we understand all the problems and all the key features of joint distributions. So let us start with our first example of whatever we have studied till now. So let me first write down the entire problem and then we can discuss. Not y, actually it should be 1. So this is the question. So I will just state the whole question and explain it to you first, and then I'll give you like a minute or so to try and figure out the method of approach or how we are going to actually attack all these three different problems associated with this statement. So it's given that x and y are two jointly continuous random variables. So it means that x and y are random variables and they are jointly continuous. So they are associated with each other and they have a common PDF. So that joint PDF is basically f of x comma y, which is a multivariate function. And when x and y both lie in the range 0 to 1 inclusive, we have the PDF as x plus cy square, where c is some real number and it is 0 otherwise. So what we do understand is it is only possible inside the range where we have 0 comma 1, right? So one thing is clear that if you have this graph here, So inside this rectangular region, the joint PDF fxy is defined as x plus cy square, and otherwise in outside of all the regions, outside of this region, in everywhere it is 0. So that's basically what the problem says. Anyways, so this is the statement, and then we have three problems. We have to find the constant c, we have to find the probability that 0 less than equals to x less than equals to half, and 0 less than equals to y less than equals to half, and also we have to find the expected value of x into y. So I'll give you like 1 or 2 minutes, probably 2 minutes, to try and think a solution to the first part, and then I'll solve it. Okay, so I think this is enough time to make sure that you have found a solution. So even if you have not, nothing to worry about, because we're going to learn it, and once you learn it, I do not think there would be any problem in solving any kind of problems like this from now on. So well, first let me write down the PDF again. It is x plus cy square only when x comma y belongs to 0 comma 1 squared, right? Now we see that in order to find this this constant c, we can use a condition that total probability is always 1. And how do we use that? So see, so since total probability is always 1, we understand that the integration over the region 0 comma 1 to 0 comma 1, that is the rectangular region of the joint PDF, would result in a 1. Now how do we do that? Well, it means that 0 to 1 and 0 to 1, because x and y are independent of each other, right now, so we can write it directly as x plus cy square dx dy equals to 1. Now, so the inner integration turns like this. It's with respect to the variable x. So obviously integration of x is from 0 to 1 is 1 by 2, and for cy square it just remains as cy square dy equals to 1. And then again we have 0 to 1 half dy plus c times 0 to 1 y square dy equals to 1. Now this gives us 1 by 2 plus c, and this is y cube by 3 from 0 to 1, right, because the integration for y square is basically y cube by 3. Now 1 by 2 plus c by 3 is equals to 1. This gives me c by 3 equals to 1 minus 1 by 2 equals to 1 by 2, and therefore from this equation we get the value of c is 3 by 2. So this completes our first part. Now let's go to the second part. We are required to find this. Of 0 less than equals to capital X less than equals to 1 by 2, comma 0 less than equals to capital Y less than equals to 1 by 2. And since we already know the joint PDF, it's easier for us to find this, because this only equals 0 to 1 by 2, 0 to 1 by 2, the joint PDF, which is basically x plus 3 by 2 y squared dx dy. And from this we get the outer integral remains intact while the inner integral evaluates like this: x square by 2 plus 3 by 2 y square from x equals to 0 to x equals to 1 by 2. Okay, and dx dy. So the plus 3 by 2 y square just remains same, and this one is basically I of x. So anyways, this becomes 0 to half. For the x square by 2 part, it becomes 1 by basically 2 cube minus 0, and this one becomes 3 by 2 y squared into 1 by 2 dy. So the x part is completed. Now this means it's 0 to 1 by 2, 1 by 8 plus 3 by 4 y squared dy. Therefore it becomes 0 to 1 by 2, 1 by 8 dy plus 0 to 1 by 2, 3 by 4 y squared dy. Now 0 to 1 by 2, 1 by 8 dy is simply 1 by 16, and this one is 3 by 4 comes outside, and integration of y square is y cube by 3, and it is from 0 to 1 by 2. So let us do this one. 1 by 16 plus 3 by 4 multiplied by, now this becomes 1 by 3 into 8, and the 3 is cut off, so it becomes 1 by 16 plus 1 by 32. On simplifying, you see that this is 3 by 32, which is the answer for the question. So We have solved it successfully, and now it's time for finding part C. E of xy is given as, now we are going to use the limits over all the integrals, over all the region basically, because we would need it to be 0 to 1, 0 to 1, xy, fxy, x comma y, dx dy. Now this is going to be a long integral because let's see, 0 to 1, 0 to 1, xy times x plus 3 by 2 y square dx dy. We can separate it into two integrals as follows: 0 to 1, 0 to 1, x square y dx dy plus 0 to 1, 0 to 1, x y cube into 3 by 2 dx dy. Now you see this x and y here are independent and they can be multiplied together, so we can evaluate the integrals of x and y separately and multiply them together, right? So this becomes 0 to 1 x square dx multiplied by 0 to 1 y dy plus 3 by 2 0 to 1 x dx multiplied by 0 to 1 y cube dy. Therefore 0 to 1 x square dx is simply 1 by 3. Okay, let me just write it correctly. One by 3 multiplied by 1 by 2, and this one would be 3 by 2 multiplied by 1 by 2 multiplied by 1 by 4. So it becomes 1 by 6 plus 3 by 16, and they have a common LCM of 48, so it's basically 8 plus 9, which is 17 by 48, which is the answer, and thus this is the joint expectation of the variables. And you see that this kind of integrations require a lot of different kind of techniques and stuffs. So anyways, the video for integration would also be embedded at the end, and you can watch that, so that you do not have any doubts regarding integration, because I do that in every video, and same for this video, it's also attached at the end. And integration in multivariate calculus is basically something like, as we have done in previous sections, it won't be like the usual way where we basically do an integration without any justification, but it would rather be something like that of the differentiation parts, where we used to define everything, we used to have a proof for even the simplest of things. So we are going to basically discuss how Riemann actually came up with this integral, how we can use that to integrate functions that we do not really do in our integration course in single variable calculus. Like you do not really know how to integrate over a rectangular region, right? You do not study that there. Neither do you study if an integral converges or diverges. So there are multiple aspects and multiple angles to a single problem, and this integration section is going to deal in general each and every one of them, single variable, multivariable, both. So let us begin. So the definition of an integral function f from a to r is, where a belongs to r to the power n is a closed rectangle, is so similar to that of the ordinary integral, that is a rapid treatment. So what we do is as follows. Let us say f is a function from a to r, where a is a proper subset of r to the power n. Okay, so f is a function which goes from r to the power n to r basically, and this function f, this can be basically treated like a multivariate function with n inputs, so n composite functions maybe. So there are multiple ways to define that, but what we are considering here is that A is a proper subset. Okay, that A is a proper subset, and we are going to do an integration over this region. Now recall that in case of a single variable calculus, what we used to do, so let us not mess with for a second that A is literally a r to the power n subset, but let us just consider it as a subset, and we are trying to reciprocate what we are going to do in single variable calculus. So what we used to do is, the integration region is a comma b closed, okay, where a and b are finite real numbers. So let's say this is the integration region. Then the partition p of a closed interval ab is partition P would be defined something like this. We are going to say A is the first point, which we name as T0. Then we have T1, and all the way up to we have Tk, where Tk is the last point, which is P. So how many subdivisions are there? So the divisions are, so the partitions are all of them are disjoint, and their union gives you the actual set which has been partitioned. That is why it satisfies the definition. So it's basically like this: A comma T0 union T0 comma T1 union T1 comma T2 union, and all the way up to union of Tk minus 1 comma B, where B is basically Tk, right? And here A is T0, so this interval is basically singleton. Anyway, so this is what comprises A comma B. So T0 to T1, T1 to T2, like there are k intervals, so there are k subintervals. And what we used to do there was basically we needed to understand that these partitions act as a rectangular region where we used to find the area, and we need to approximate it, and then we used to tend the number of these partitions. So basically we used to increase this number of partitions, which is k right now. We would let k tends to infinity so that the approximation becomes like more clear and it becomes more transient throughout time, and that is how we would get the actual value of the integration when we have the limiting value. Now when it comes to this nth dimensional things, what we can do is we can divide this A, which is a subset of r to the power n, into n subintervals, right? So what we can do is something like this. We can write for A, which is a subset of Rn, r to the power n, we can write P is basically the partition of P1 cross P2 cross P3 and all the way up to Pn, where each of the Pi's are themselves partitions, okay? And this A is a closed rectangle, as I have already told. So A is basically a closed rectangle, so all of these Pi's can be partitioned, right? Now what we can do here is we can divide them into ni subintervals, each of them. Basically what we can do is, if Pi divides small ai comma small bi into ni subintervals. Now if that happens, what we can do is we can say that this sub intervals, which is basically what we can do is a1 ti comma 1 I comma I minus 1 to ti. Let this be the sub intervals, number of sub intervals for I equals to 1 to n for p1. Similarly, let if s is another variable, we can write si comma 1 to si for I equals to 1 to n. This is for p2 and so on and so forth. So each of these pi's are different partitions, and they divide this integral region or this closed rectangle A into a finite number of disjoint subintervals themselves. Each of the pi's divides them into ni more rectangles, right? So this is how we can partition the multidimensional case by breaking it down into the single dimensional case. Now what we can do more is as follows. Let S be the subrectangle rectangle corresponding to each pi. So for a particular pi, we pick a subrectangle S, in which it is which is being partitioned basically, and what we can calculate for that is the smallest ff, which is basically the infimum of the set and the capital M, which is the supremum of the set. Once we calculate this two, now let V of S be the volume. Let so this is the rectangle a1 comma b1 cross a2 comma b2 and all the way up to an comma bn. Now the volume of this is defined simply as b1 minus a1, b2 minus a2 and all the way up to bn minus an. Okay, now the lower and upper sums of f for p are defined by, this is very important, lower sums and upper sums. Lower sums and upper sums. So the lower sums and upper sums are defined as follows. L of f corresponding to the partition P is basically summation over the set S, which is the subrectangle correspondingly right now, over all such subrectangles S, ms of f multiplied by volume of S. And similarly the upper sum is basically summation over S capital ms of f multiplied by v of s, right? And clearly small s of f is less than equals to capital ms of f, because this is the infimum and this is the supremum. Therefore L of f comma p is less than equals to u of f comma p, right? So what this like does mean is that obviously the lower sum is less than the upper sum, but it also means that if you have another partition p prime which basically defines p, that is the each subrectangle of p prime is contained within a subrectangle of p, then we can also say that the lower sum of p prime is greater than the lower sum of p, and the upper sum of p prime is less than the upper sum of p. So that is also one of the ways to do this problem and understand these properties of lower sum and upper sum. Basically, what we are doing is we are taking each subrectangle. We are trying to find the infimum in that. We are trying to find the maximum in that, or the supremum, and we are trying to multiply it for each subrectangle. We are multiplying in the lower sum the infimum of the rectangle multiplied by the volume of the rectangle. Then we move on to the next success of the partition P, and then we do the same and we add them all up, and this addition, whatever it gives you, it is called the lower sum. Similarly, when you take the supremum, it is called the upper sum, right? So what we can actually understand is as follows. So what we say is that a function f from a to r, where a is a subset of r to the power n, basically is called integrable on the rectangle A if f is bounded. So firstly, the condition is f must be bounded. Secondly, you find the lower sum and the upper sum corresponding to a partition P. The partition is for up to you to choose, and what you need to check is that the supremum of the lower sum and is equal to the infimum of the upper sum. Then the common number is basically called the integral, that is supremum of lower sum equals to infimum of upper sum, and this is basically called the integral of f, right? So how do we basically understand if a function is integrable? This is the condition, but there is a much easier condition to follow which we are going to study now, and that condition would clear a lot of the doubts and would give us a really powerful tool to work with. So let us see that. So the criteria for integrability. So upper sum of f comma p minus lower sum of f comma p less than epsilon. So let me just restate it again. A bounded function f from a to r, of course where a is a subset of r to the power n, is integrable if and only if for every epsilon greater than 0 there exists a partition p of a such that the upper sum minus the lower sum is less than a certain epsilon. Firstly, we do not need the modulus on this because the upper sum is always greater than the lower sum, so this quantity is always positive, and we want it to be less than epsilon for an arbitrary epsilon which is a positive real number, right? And we want that there exists such a partition p of the subrectangle a so that this happens, and this condition is enough for for us to have basically that this is an integrable function. So we can do some examples now to understand in clear, because only by examples and applications we shall understand how to use this kind of problems, right? So in the first one we can do something called a constant function. Where c is a constant obviously. Is integrable. So this is the most basic example we could find. Of course another basic would be to calculate the integral of fx equals to 0, but that is the same as the c, right? Because c can be 0 as well. So what we are doing is we are calculating where fx is equals to a real number. We are calculating the integral of that. So then for any partition p of a, what we will have is that the subrectangle S, in any subrectangle S we will have the infimum and the supremum both equals to c, because fx is just the constant function, right? So the value of f is always right. So what is the lower and upper sums? The lower sum is it would be something like this. Sorry. So this is the expression for the lower sum. Let us calculate it. So for each subrectangle S we have the minimum, that is the infimum, is basically c. And what about the volume? We do not know the volume yet, but what we understand that when we add all the volumes over all the subrectangles, and since c is a constant, c comes out. So over all subrectangles the volume of S, if you add them all up, it will be c into v of a, right? Similarly for the upper sum, and since it is also c, it comes out and you get c of v of s, which is c into va, right? And we can see that the supremum of the lower sum is equals to the infimum of the upper sum, because it's just c into va, both of them. Therefore integral of f over integral of f over the region A is basically C into V of A, which is the volume of A. So I'll just give you a moment to process this one. We'll start another example in about 10 to 15 seconds. So just take a look at this lower sum and upper sum calculation. So let us do another example. This one is a bit of a classic because you have done it in the single variable case. Now we are going to do it in this multivariable case. Let me write down the problem. Let this would be this, sorry, P now what we can do is we can partition x, obviously, because we have a rectangle 0.0, into 0, 1, and what we can do is we can partition it. And for any partition p, we do not really need to mention the partition because it's arbitrary, you know that. We can partition into k subintervals and stuff like that. But what we can do is every partition, where in every partition basically, so for a partition p, for every subrectangle S, we have for every subrectangle S we have the partition, let's say ai comma bi, will contain both rational and irrational points, right? So will contain and irrational points. So what we do understand is that ms of f will always be 0 while capital ms of f will always be 1, because for every partition you make, the maximum you can go is 1 and the minimum you can come is 0. So it doesn't matter what the other values are, because the infimum is basically the lowest you can reach, so it's always 0, right? So therefore but since the infimum is 0, this is 0, this becomes 0. Similarly, the maximum is 1 into the volume, and the volume of A is simply 1, because you know that the volume of 0, 1, 0, 1, it's basically in this space. If this is 0 and this is 1, and if this is 0 and this is 1, it's basically this rectangle, right? This rectangle has area of 1, so volume in 2 dimensions only means the area, which is 1. So therefore this is not integrable, because we see that infimum of upper sum not equals to supremum of lower sum. So f is not integrable, right? So that much we do understand. So I'll write the problems one by one and then we can solve them and understand them clearly, thoroughly with each step. So here goes the first problem. So this is basically the first problem which we are going to do. So carefully read the problem first and then I shall read it and explain it to you, and then we shall move on to the solution. I give you 10 seconds to read the problem and understand it. Okay. So we see the problem saying is that the function f of x comma y has been defined like this, and that we need to show that f is integrable and the integral over f over the region which the domain is defined is equals to half, and the function is a piecewise function which is 0 if x like x is from 0 to half, and it is 1 if x is from half to 1. So let us do all the necessary pre-bindings first, and I shall write down the solution, then I shall explain it. So the partition P is composed of two other partitions, P1 and P2, and this is because we see right here that P is a partition and we need two partitions for our case, because you know the domain is 0 comma 1 cross 0 comma 1, which is the R squared, so it's a subset of R squared, right? Because a region here, because our integration region here is just a equals to 0 comma 1 squared, which is basically a subset of r square, so it belongs to r square, right? So obviously that's why we need two such partitions, and using two such partitions what we can do is as follows. L of f comma p would then be summation over all such subrectangles 0 comma s infimum of s of f multiplied by the volume of s, right? Now what we can see here is ms of f. So there are two rectangles, right? So we actually do not need to do it for each rectangle, but we can do it directly. So for the first rectangle, which is this 0 comma 1 by 2, the minimum is 0 and the volume is half minus 0, right? So and for the second rectangle it is from half to 1, the infimum is 1 by 2, while this basically here it's basically 1, right? The volume of s is 1. So it becomes 1 by 2. And similarly for the upper sum, we have for 0 comma 1 by 2 it is 1 by 2 into 1 by 2, and for the other part it's also again 1 by 2 into 1 by 2, so it's 1 by 4 plus 1 by 4, which is 1 by 2. And so we see the lower and upper sums are equal, and therefore is 1 by 2, right? So this is basically the Riemann condition, and from the Riemann condition we understand that this is how we can evaluate this lower sums and this upper sums, right? Okay, now this is how we do this first sum. Let us move on to the next one. Let me write down the problem, and this is going to be a difficult sum, a much difficult sum than the previous one rather, so we are going to need to focus on this one. So we need to show that G is integrable and that the integrals are equal, right? This is what we need to show. So the goal of this problem is to let you know that if one of the functions are integrable and there is another function which is equal with this function, which is basically this function, except at finitely many points. When I say finitely many points, I mean for a countable set of points the functions are not equal, but for infinitely many of them they are equal, right? So when I say that, it means that the integral of those two functions are basically equal, and that's what it means to show this problem. So let us begin. We know from the Riemann condition the following things, and we are going to write that. So let me just write down the solution one by one. So first we are fixing an epsilon greater than 0, because this epsilon should be a real number. Less than epsilon greater than 2. Now, since we know that the partitions should be different for f and g, because what we understand is that g is not equal to f at finitely many points, right? So if we are going to integrate f with the partition p, then we should need another partition p prime. So we consider p prime to be a refinement of p such that So what do we mean is, we consider p prime to be a refinement of p such that for every x belongs to a, where a is the integration region with g of x not equals to f of x, so we are considering all the points x where the functions g and f are not equal, and we are saying that it belongs to 2 to the power n subrectangles, so it should be subrectangles actually, subrectangles of p prime, which is the new partition, that is x is a corner of each such subrectangle, right? So basically for each subrectangle, so for each subrectangle S of p prime, we are defining this, and let me define the terms here. So these are our definitions, right? And this partition is made such that the volume of each subrectangle is less than epsilon, and you see the epsilon by 2 from here comes from this epsilon by 2, and it gets multiplied with 1 by 2 to the power n d of u minus l. So what we are trying to find here is that we are dividing the whole region into sub-regions where each rectangle has an area of 1 by 2 to the power n, because there are 2 to the power n sub-rectangles, so each one will have 1 by 2 to the power nth of the area. And we are also multiplying, basically dividing by d of u minus l, where u is basically supremum of gx minus infimum of fx, where l is infimum of gx minus supremum of fx. So okay, so this should be fx, obviously this should be f of x, right? So this is what we have in mind. Now for that, what we have here is this. We can say the upper sum of g with respect to p prime minus the upper sum of f with respect to p prime would then mean right. And here obviously v is supremum of s belongs to p prime of v of s. So v here denotes basically the supremum of the set of the subrectangle S, which belongs to p prime, obviously, of the volumes of S. So v represents the highest number of volumes here, where v is defined as follows. We use v here. Like this. Okay. So it's basically the least upper bound of the volumes of the subrectangles of p prime. Similarly, what we can also do is as follows for the lower sums. Where we also find that v is the supremum again. So basically what we want to understand here is we wanted to find u of l minus g of l, right? So ultimately we can show that u of g minus g of p prime, so the upper sum of g with respect to p prime minus the lower sum of g with respect to p prime is equal to this definition limits, right? So upper sum of g of p prime is basically summation over all rectangles right. And from this above 2, what we can see is that u of g comma p prime and minus u of f comma p prime is basically this is less than equals to this, and this is less than equals to this. So obviously this would be less than equals to like this. So u of g comma p prime is less than equals to this part only, less than equals to u of f comma p prime plus d into 2 to the power n into uv, right? and this part is greater than equal to right. And so since it's a minus, so this part is greater than equal to this part, so minus of this should be less than equals to minus of this part, right? And now we can write this as follows: u of f comma p prime minus l of f comma p prime plus 2 to the power n dv into u minus l, and this part is again less than equals to epsilon by 2, so it's epsilon by 2 plus 2 to the power n dv u minus l. But we know that this v is less than this volume, v is less than a particular thing, so what we can do is this epsilon by 2 plus 2 to the power n into d into u minus l, and v was less. If you can go above, what we can see is that v is less than epsilon by 2 to the power n plus 1 d into u minus l. So epsilon by 2 to the power n plus 1 into d into u minus l, right? And therefore this cut off to give you a t, and this both cut off, and what you get is epsilon by 2 plus epsilon by 2 equals to epsilon. So therefore it is integrable. Therefore g is integrable. And now it is obvious that integral of f is equals to integral of g. So you see that this kind of problems make a lot of sense when you try and implement them with the functions from Riemann integration. And obviously since you have multivariate calculus here, it becomes a little too messy, but obviously that can be overcome very easily. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems in theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.